All right, here we are in the middle of another AP chemistry lecture. So we're trying to figure out how much energy it takes to break a chlorine-to-chlorine bond. So given this, we're changing kilojoules per mole into joules per electron, joules per photon. And what number did we come up with?
4.02
times 10 to the negative 19. And that's just joules, and it's technically joules per photon, but photon isn't a real unit, and so we just say joules. This is the E, this is the energy of one individual photon. Anytime you put it into this equation, it's always per photon, not per mole of photons. Okay? It's pretty straightforward conversion. This is very, very common that you need to be able to do this. Okay, so maybe put a star by it and tell yourself that you need to know this stuff. Okay? Now I can just plug in. Well, these two are constants, so it's going to be given 6.626 times 10 to the minus 34th joules seconds times the speed of light, 3.00 times 10 to the 8 meters per second, divided by the energy we just calculated per photon, 4.02 times 10 to the minus 19 joules. Notice that seconds are going to cancel there, joules cancel here. We're left with meters, which is a measure of wavelength. What does that come out to? Did anybody already do it? 4.56 times 10 to the minus 7. 4 point what? 4.94 times 10 to the minus 7 meters. But generally we do light for visible light in terms of nanometers. How many nanometers are in a meter? 10 to the 9th. Now it seems to me like there's one question on AP tests in the past couple of years where you actually had to know that. Okay? Nano is 9. Nano is 9. So if we multiply this by 10 to the 9th nanometers over 1 meter, what do you do when you multiply exponents? You add them. Okay? So this is just going to be minus 7 and 9, so it's going to be times 10 to the positive 2, which really means that this is going to be 494 nanometers. So you can just come over here and you can look on the spectral chart right here, and you'll find that 494 is going to be right here in this light blue. So it would take at least a light blue. Red, yellow, orange, green, none of that's going to break the chlorine to chlorine bond, but yet you get into the light blue, anything with a wavelength of 494 or shorter. Remember, if you're given this equation, what's the relationship between energy and wavelength? As wavelength gets bigger, what happens to energy? It gets smaller, right? So shorter wavelength means higher energy. Energy and frequency are directly proportional. Higher frequency equals higher energy, but wavelength and frequency are inversely proportional. So the longer the wavelength, the lower the energy. So red's going to have your longest wavelength. Blue is going to have your shortest. Okay? You're not following me very well. So we can just kind of go through and calculate this. So you are going to need to be able to do these types of calculations between energy, wavelength, and frequency. Given this, the biggest thing is always know that energy is in terms of joules per photon, not kilojoules per mole. If it's kilojoules per mole, you just got to do this conversion. Sometimes, if you did it in reverse, the answer comes out to joules, but they want it in kilojoules per mole. So then you just go in reverse. You just convert, multiply instead of divide instead of multiply.
Will they give you E equals H or lambda on the AP test?
No. But it's very simple. I mean, you could just do it in 2 steps if you don't have that, or you can, again, this is the common variable, so V nu is equal to C over lambda, and that's what it plugs in. I've always just pretty much done it in 2 steps. Anyway. So we understand now the nature of light. Light has a dual nature. It's got a particle nature and a wave nature. So we're trying to figure out then, okay, well, how is light produced then? Rutherford, well, first off, Thomson discovered the first subatomic particle using the cathode ray tube. It was an electron. Then they knew that if that's a negative particle, there has to be a positive something or other there. Thomson had the plum pudding theory, which you had the dough, and then the raisins on the outside. I think more like cinnamon roll. That's more my genre. You know, I'm not sure what plum pudding is. But, you know, the dough with the raisins on the outside, the raisins were your electrons, because he could knock them off easily in a cathode ray tube. But then Rutherford did his gold foil experiment, where he shot the alpha particles at the gold foil. You guys remember that? And the nucleus was very, very tiny, very dense. Most of the atom is what? Empty space. So this table is mainly empty space. Mainly empty space. I think some emptier than others, okay? Mainly empty space, okay? And so he came up basically with a planetary model where the electrons are outside in this kind of like planets going around the sun. But classical physics said that if you have a charged particle that's rotating, that it ought to radiate its energy, and it ought to radiate it and go crashing into the nucleus. So we had a problem in that the electrons don't do that. So Niels Bohr came, he was a Danish scientist. Rutherford was a big experimenter. Bohr was much more of a theoretician. Bohr came to work with Rutherford, and they were trying to figure this, the structure of the atom out. And they had, is this hydrogen? Did you put hydrogen in here?
I didn't put anything in
Okay,
there.
I think it's still in there. Okay, so everybody get some of those glasses out. Okay.
What I was doing.
Ooh, it's dark. But we turned the light on.
That's what I was doing.
Does it work?
Not really.
Okay.
Unfortunate.
When you look at this with the
Video people
glasses,
cannot see.
does everybody see out to the side the red line? You have a kind of a teal greenish bluish line, and then a violet line. And then you probably have a whole series of those, but you should see a predominant. Now there's probably some stray light because coming in from the outside, but you should see a red line, kind of a teal colored line, and a violet line.
Oh, it's just way over there.
It's off to the side. That's exactly right. Oh, it's just way over there. It's weird that it's off to the side. Now what you have on are diffraction glasses. It's showing that light has these diffraction characteristics. Is everybody seeing the lines? Okay? Now, if I go and I take a different element, I can't see in the dark here. This is now very hot.
It's very hot though, so we touch it.
Okay, this is neon. Now notice neon,
Colors.
okay, again, you're seeing a whole series of lines. These are called bright line spectrum. It's not a continuous spectrum like a rainbow.
I was trying to make it.
It's a bright line spectrum, but it's different than hydrogen's. Very heavy in the red and the oranges on this one, which is why neon signs were so popular, is because they give this bright light, and so they make a great sign. Now they can make the neon lights not out of just neon, out of a lot of different elements, mix it, and get all the different colors in your neon lights. But again, they're not all just neon, but they call them neon lights because they started with neon. If I take one more, I'm surprised this one doesn't float away, because this one's helium.
Oh, it's got all the colors.
Okay?
Most of them anyway.
But again, the reality is if we had perfect diffraction gratings and diffraction scope, dark, you're going to get 6 lines with helium. Okay? 6 definitive lines in the visible light spectrum. And when you look at all of the different elements, every element has its own unique characteristic bright line spectrum. This is how they can know what elements are in the sun or in stars, because they can look at the spectrum that's being given off, and they can identify elements, because it's kind of like going to Walmart. When you scan your items, the barcode, everything's got its unique set of lines, its own barcode identifies what the substance is. Every element has its own unique set of lines, its own bright line spectrum, to where it identifies what that element is. So if you can find some element with a unique a set of lines that has never been seen before, well, you may have discovered a new element. So they're, looking out in space, they can take the light. So when they're looking at the sun, they say, okay, well, we know hydrogen has these lines, so then the computer can extract those lines out and see, well, what other lines are being given? Well, that matches up with helium, so there's a lot of helium in the sun. Take those lines out. What else? What other colors? Because every element has its own unique set of lines, and so they can figure out what the sun and different stars and what things are made up of by their bright line spectrum. It's their fingerprint. But why does it do that? Bohr worked for several years with Rutherford trying to figure this out. I know. Oh, I'm going to turn the lights on.
You can actually see the light spectrum of the lights too.
Yeah. Okay, so now you can look and see here, we're getting much more of a continuous spectrum, a rainbow, when you look at the fluorescent lights.
Oh, through a flashlight, it's like really big.
The flashlight kind of gives you a star, doesn't it? Kind of, just all over the place. He wants to see it. Shine the light in his eyeballs.
You can see the
Blinded.
ceiling ones though.
Blinded by the light.
You can see the ceiling ones.
The camera ironically can't see it.
Yeah, that's what I was checking earlier. The ceiling can see some of them.
Okay, so
over here.
when we're looking, Niels Bohr finally figured out, and we came up with this theory. Because Rutherford had the electrons going around like the planets around the sun. Physics said that they ought to be radiating the energy, crashing in. Well, Bohr looked at hydrogen over and over and over and over again, and it always gave off those same four colors. Now, the reality is that you saw a red, a teal, and a violet line. If everything was dark and perfect, there is a fourth, another violet line very close to the violet line that you could see. There's a fourth line right on the edge of our visible light spectrum. That it's got to have almost perfect conditions for us to be able to see it. But it's there. Okay? The reality is when you look at this with machines, they can detect 21 different lines. And what Bohr was able to do is he said, the electron doesn't cave in because it must have a fixed energy. Unlike anything else in physics that they'd studied at the point, he said it doesn't cave in. It's got to have this fixed energy that it doesn't lose. Well, how do I know it doesn't lose? Because it doesn't cave in. So he just said, it must not behave like other particles. So it's got its own rules. And he said, the electron must be in these fixed energy levels. Using Max Planck and what Einstein was saying, that the electron now is in fixed energy levels. And he was able to calculate the energy that the electron would have in a hydrogen atom on that fixed energy level. And he found that on the first energy level, he found his energy, that E, the energy of the electron, on any energy level is 2.18 times 10 to the minus 18th joules. That's an 8. It's a lousy 8. Minus 18th joules over n squared, where n equals the energy level. So on this first energy level, E is going to equal negative 2.18 times 10 to the minus 18th joules divided by 1 squared. So in other words, it's going to have negative 2.18 times 10 to the minus 18th joules of energy. So I know you're asking, Mr. Hobbs, how can they have negative energy? Well, the sign is always which direction is energy flowing and potential, where is the zero? It's all relative energy. Positive 2.18 is how much energy it takes to remove an electron from here, completely make it an ion, to knock it out of the orbit. Okay? Orbit's not a good word, but to knock it off the attraction from the nucleus. Okay? So the positive is how much it takes to go to here. So this, right on the edge of where the nucleus no longer holds it, is considered zero energy. So coming down, it's negative. Going up, it's positive. So it's not like it has a negative energy. It's just using this out here, the outer edge, as zero. That's how much energy you got to put the positive to make it go away. The negative is measuring the strength of attraction to the nucleus. So on the second energy level, E is going to equal negative 2.18 times 10 to the minus 18th joules over 2 squared. And on the third energy level, E is going to equal negative 2.18 times 10 to the minus 18th joules over 3 squared. To every energy level, he was able to find that the energy of each energy level, but they're fixed energies. Now, what does this mean when it goes down from 3 down to 2? What happens? How much energy difference is there going to be? How could I calculate the difference? Well, do I know how much energy it has on 3? Do I know how much energy it has on 2? How do I get the difference? Subtract. So we can say then, okay, you guys all have that. Delta E from 3 to 2 is going to, and he found it's always E final minus E initial. So it's going to equal negative 2.18 times 10 to the minus 18th joules over final is going to be 2 squared minus negative 2.18 10 to the minus 18th joules over 3 squared. Somebody put that in the calculator for me, please. Give me a number. N is the energy level. So we're going from the third to the second energy level. Seriously? Only 7 minutes left?
What's the significance of the negative 2.18?
That's just what Bohr found in terms of the energy. That was in his equation. He found out that's how much energy an electron has on each of these. And I'm just going to kind of expand on this as soon as we get some numbers. Do I have 2 people agree on a number?
I got negative
3.03 times 10 to the 19th?
Yeah.
Negative 3.03 times 10 to the minus 19 joules. So what does that mean? Bohr found that when the electron goes from the third down to the second energy level, it's going to release a photon that has that much energy in it. Now, what does the negative sign mean? The negative sign simply means that the energy is being released. If we were going from the second up to the third, we're just going to flip everything. We're just going to change the sign. We would put in positive 3.03 times 10 to the minus 19th joules. That's what the electron would absorb to go from the second to the third. So every time an electron transitions, so the electron normally wants to be down here, the ground state, lowest possible energy state. But when you put electricity or heat onto the electron, it causes it to absorb energy and go to a higher energy state. And then it just naturally is going to want to come down. When it comes down, it's got to release the energy that it just absorbed. So Alabama Power is putting the energy in. The electrons are going up. and then they just naturally come back down, and when they do it, they release the energy that Alabama Power just put in. Now, in an old incandescent light bulb, just the normal with a filament, it released a lot of the energy as heat instead of light. So a lot of the energy was wasted. We're trying to make light, but a lot of it was wasted as heat. So a fluorescent light bulb has a gas in it, just like this with a vacuum, but it's got different gases in it. That's why if you look, these older lights kind of have a pinkish tint to them. Do you see kind of the pink tint versus the one in the middle? I think that's, and maybe this one over here, that's a little bit more white, a little bit more, actually a little bit more blue to it. They're different lights. And if you ever go to Home Depot or Lowe's or you go to buy a fluorescent light, you got soft white, cool white, night white, day white, you know, and it's all depends upon what gases, what mix of gases do they have in there that are gonna glow the different colors. They also have the white coating on the inside, then that absorbs those photons, then they re-release it more of as a white light. From what I've been told, if it didn't have the white coating on it, most of the light, most of the energy is given off in UV. And then the fluorescent, the white coating absorbs that and then kind of does a glow in the dark from there. So, but they all have different gases in them, they glow different colors. I do believe that these lights here, the pinkish ones, I've been in this room since the school opened 21 years ago, 22 years ago. I don't think they've ever been replaced. The ones that are the different colors are the ones that have gotten replaced, which really says a lot about fluorescent lights as far as their efficiency. LED lights are even more efficient. They're converting all of the energy into light. But all light is produced by exciting electrons up, and then they just naturally fall down. So this is, they fall down by giving off photons. So this is the energy of one photon. Well, that photon has a certain wavelength and frequency. So I can calculate now the frequency, because frequency is going to equal E over H. Now you don't have a negative frequency or wavelength. The negative sign simply tells me that the energy is being released. So I can drop the negative sign off here. So I can simply say 3.03 times 10 to the minus 19th joules divided by 6.626 times 10 to the minus 34th joule seconds. And I can get 3.03 EE, trying to do this with eyeglasses is not good, minus 19 divided by 6.626 EE negative 34 equals 4.57 times 10 to the 14th, and joules are going to cancel. That's going to be per second, which is a hertz. That's the frequency that the photon is going to be traveling in. Well, I can now find the wavelength of that, because wavelength is going to equal C over lambda, C over nu. So it's going to be 3.00 times 10 to the 8th meters per second divided by the frequency I just found, 4.57 times 10 to the 14th per seconds. Seconds are going to cancel, leaving me meters. I don't think I can do second function answer on this. So it's going to be 3 divided by 4.57, 14, and I'm going to get 6.56 times 10 to the minus 7th meters, which is equal to 656 nanometers. Okay, big deal, Mr. Hobbs. Well, I come over here and I look at 656 nanometers, and I find that's right there on the red line. So that tells me that when an electron is transitioning in hydrogen from the third down to the second energy level, that's the red line that we're seeing given off when we look at the hydrogen spectrum. Every time we put that electricity onto hydrogen, the electrons are going up and down. Whenever it goes from 3 to 2, it's giving off photons, which then are hitting our eyeballs. We're seeing as red, the red line. Now, way back when, right after electricity was created, and I was in high school, we put electricity onto hydrogen, and it gave those exact same colors. Then I went to college. They gave exact same colors. Then in a galaxy far, far away, a long, long time ago, in a place called Louisiana, I taught and I put the hydrogen under electricity, and we saw the exact same colors. Whenever it goes from 4 to 2, it's giving off the teal line. Whenever it's going 5 to 2, the violet line, 5, 6 to 2, the other violet line, 7 to 2, just barely into ultraviolet. It never gives off any other colors in the visible light spectrum. It gives off all these in the infrared, it gives these off in the ultraviolet, but only these. What does that mean? The electron can only gain or lose a specific amount. It's quantized. Quantum means specific amount. The electron can't just gain or lose random amounts of energy. If it could go from here up into somewhere like right here in the middle, and then just come back down, that would be some other color. That would be like green. Well, hydrogen never ever gives off a green light. What does that mean about the electron's ability to have that much energy? Can't do it. It can only go from one fixed energy level to another fixed energy level to another, to another, to another, to another, to another. Nowhere in between. It's like trying to climb a ladder. You can't go in between rungs, otherwise you're going to be in trouble. You're going to go one step to the other. Now notice that they're not evenly spaced, because you're going from 1 squared to 2 squared. You're dividing by 4, so there's 4 times difference between these two. But you're going from 2 squared to 4 to 9. Now there's only 2.5. Then you go 9 to 16, and it's not even double. And then 16 to 25. So that's why the energy levels are getting closer and closer, because you're dividing by the square. Y'all have a great weekend. It's homecoming. Be safe, make good choices. If you can't be good, be careful. Okay? Come back all in one piece on Monday.